In this video, we're going to look at limit laws, examples where we exercise the limit laws. So let's start with the first one, which is the constant rule. And it basically just tells us that the limit of a constant is that constant. So we have an example here of that. And the limit as x approaches 2 of pi, and it turns out that's equal to pi. Now, the fact that we're looking at when x approaches 2, that doesn't really matter. The limit of a constant is that constant. It doesn't really matter that x, whatever x approaches. But let's just think about why is that true. Okay, so if we look on the curve, you can see I've graphed the curve here, which is just a horizontal line, y equals pi. And if we trace along the curve from the left, that's in dark green here, letting x approach 2 from the left, then the y values are, of course, are staying constant at pi. And then similarly, if we look at things from the right, that's in light green. Then if we trace along the curve, letting x values approach 2, then still the y values are always pi. So the trend there is always pi. All right, so that's the first one. The next one is the sum rule. And we have an example of that. And so that just basically tells us that, so if the limit here of x squared plus 3x is equal to the limit of x squared plus the limit of 3x. And then that's the limit of x squared as x approaches 1. Well, that's going to get close to 1. And then as x approaches 1, the limit of 3x is 3. And so that's equal to 1 plus 3. And then very similar for the difference rule, I think is what we called it. That's here. So if there's a minus there, it just propagates throughout like the plus did. So very similar. In fact, those two rules could really be combined because we know that addition is really just, subtraction is really just the addition of a negative. Okay, so that's rule 2. Let's see, I have rule 3 somewhere. Oh, there, okay, there it is. And so rule 3, recall, that's the constant rule. So that tells us that if we're taking the limit of a constant times a function, then that constant can be brought to the front. And then we get k times the limit of f of x. So let's look at a simple example of that. So here we have the limit of 5x squared as x approaches 2. And so the 5 can be brought out to the front. And so we have 5 times the limit. And the limit here is 4, so 5 times 4 is 20. Okay, so that's the constant multiple rule. And then the product rule is similar. In fact, the constant multiple rule is an instance of the product rule. But with the product rule, it's really useful if the two functions are variable, if they change, with x at some point. Like before, with the constant multiple rule, the 5, that doesn't change with x. So the 5, the constant, can be brought out in front. But like here we have x squared times sine of x, and those are two functions whose values change with x. So that's when you would want to use the product rule. All right, so that's equal to the product of x squared times the product of sine of x, both of these as x approaches pi over 2. And so for x squared, that's going to get close to pi over 2 squared. And then the limit of sine x is going to get close to the sine of pi over 2. And so the sine of pi over 2 is 1. So then that's just equal to pi squared over 4. Okay, so that's a couple of videos. That's a couple of examples so far. Let's see what we have left. We have the quotient rule, the power rule, and the root rule. So I have an example of each one of those. So let's start with the quotient rule. So here, number 5, we've got the limit of x plus 2 divided by x minus 1. And as long as this bottom, the denominator part does not limit to 0, then, and the assumption here is that the limit in the numerator exists and the limit and the denominator exists both, then we can say that that's equal to the limit of the top divided by the limit of the bottom. And so in this case, the limit is 5 divided by 2. Okay, and then 6 is the power rule, I believe. Let's see. 6 is the power rule, yes. And so here we've got sine of x to the second power, and we're looking at the limit as x approaches pi over 4. And so that's equal to the limit of sine of x and then that squared. And then the limit of sine of x as x approaches pi over 4 is the sine of pi over 4, which is the square root of 2 over 2. And so we get 1/2 for the answer. Okay, so that's the power rule. Now let's look at the root rule. That's the last one, and the root rule's it's pretty, a little complicated. So let's look at each one of the, or let's look at it in more detail. Let me zoom back in just for a second. So what we have to be careful of here is we have to steer clear of the situation of taking the square root of a negative number. So we have to steer clear of complex land, is the way I usually say it in class. So if n is odd, if our root is odd, and then we have no problem, because we can take an odd root of a negative number. But so when we really have to be careful is if n is even. So if the root is even and the function itself, the part under the radical, limits to a positive value, and it does have to be positive to use this rule, then we can bring the limit, under the root, under the the root, and then proceed from there, and you get this answer here, whatever that is. But again, if this function under the radical limits to 0, then we're going to see that can sometimes cause a problem, and so we can't use this result here if L is 0. Again, if the function under the radical limits to 0, then we have to use other methods. We can't use this rule. Okay, so let's look at some examples. I actually did 3 for this one. Let's see, that's a little too big. There we go. All right, so first, if we look at the limit of the cube root of negative x squared, so this is a case where we're looking at an odd root, then no problems. We can just bring the limit under the radical and get the answer there of negative cube root of 4. All right, so let's look at part B. So part B is a situation where the root is even, but so then we have to focus on the part under the root, the sine of x. And the limit of sine of x as x gets close to pi over 2 is 1. So that's a case where we can use this because this is a situation where the L value is positive. So from there, we can bring the limit under the radical and get the answer there. And then for part C, we're looking at the limit of the same thing, but now as x approaches pi instead of pi over 2. Well, now let's see, the sine of pi, that's 0. So that's a situation where the L is 0, and so that's a case where we cannot use the theorem. And what we have to look out for is, like I said earlier, the situations where we're dealing with the square root of a negative all the time. And that is the problem here. And so this limit does not exist, so just to be clear. So let's look at the graph of the sine curve. So here we are at 2 pi, there's pi. And remember the period, so I'm going to graph y equals sine of x. And remember it has period 2 pi, amplitude 1. I'm not going to write that down, but we know that. Okay, so sine of x at pi over 2 goes up to 1. And then it's at -1 at 3 pi over 2. And so it looks something like this. And keeps going on each side in that wavy pattern. And so the problem is that since we're taking the limit as x approaches pi, then on one side, right, let's look at things from each side. So from the left side, let's go with a different color. From the left side, the sine values are positive. And there's no trouble there. But the problem is from the right side. Right, from the right side, values are negative. And since the values are negative from the right, then that totally messes up the even root, and so that we don't have a limit in that case.